Now, for the next part, we talk about wave-particle duality. Wave theory provides good explanation for phenomena such as interference and diffraction, but it is unable to explain the photoelectric effect and light spectra. To be able to explain them, we have to consider EM radiation, such as light, as particles of energies called photon. Now, to that effect, light interacts with matter such as electrons as a particle, but it propagates through space as a wave. This is known as wave-particle duality. Now, a scientist named Louis de Broglie proposed that just as light has a dual nature in the sense that it can behave as both a particle and a wave, depending on the situation, particles such as an electron might behave as a wave too. He proved this by showing that a diffraction pattern is produced when a beam of electrons is directed at a thin graphite film. Now, why do we want to specifically talk about diffraction here is because diffraction is a property of waves and cannot be explained when electrons behave as particles. So if we are able to see a diffraction pattern, this would mean that a particle behaves as a wave now. So in our case, we try to use a particle such as an electron and see whether a diffraction pattern is observed. Now, to recap what is meant by diffraction that you've learned in AS, diffraction is the spreading of a wave as it passes through a slit. Say, for example, right now, you have a slit that looks like this. There's a small hole right in the middle there, and then you direct some wave towards that slit. As the wave approaches the slit, it will try to squeeze through that slit, and if it manages to squeeze through, it will diffract, it will spread into the geometric shadow behind the slit. So this is what we mean by diffraction. And to get significant diffraction, another important thing that you will have learned is that for significant diffraction, the gap width must be comparable to the wavelength. Now, what do we mean by comparable over here? Comparable here means that they must have same order of magnitude, okay? So when you talk about same order of magnitude, another way to think about it is that they must have same power of 10. That is what we mean by comparable, okay? Now, to observe the diffraction of electrons, a beam of electrons must be focused through a gap similar to their size, such as an atomic lattice. In our case, a graphite film is ideal because its crystalline lattice structure has gaps between the planes of the atoms that acts as slits, thus allowing the electrons to spread out like a wave and create a diffraction pattern. Graphite is a crystalline solid, so its atoms are often arranged in a regular repeating pattern that looks like this. So let me just draw them out first, nicely. Let's just say for the sake of our discussion, your graphite atoms are arranged in a regular repeating pattern like this. So from the diagram that you see here, you can see that there are actually vertical spacings between the atoms and also horizontal spacings between the atoms. So these spacings here act as your slits. You have a horizontal slit and a vertical slit right now, so that when you have an electron that is going towards the graphite film, it will pass through each of these individual slits. If it behaves as a wave, it will by right diffract. Okay, so if your electron diffracts right now and you place a screen right behind the graphite film, you ought to be able to see a diffraction pattern. Now, for our case, because you have a series of horizontal as well as vertical slits, you have diffraction in 3D. If the electrons diffract after passing through your graphite film, they should produce a diffraction pattern on the screen placed behind the film. So in our case, the diffraction pattern observed on the screen would be a series of concentric rings, similar to that when light passes through a diffraction grating. So right now, if you have a screen behind the film and your electrons diffract and produce a diffraction pattern, the pattern that you expect to see would be a series of concentric rings or circles like this. This is what you know as your diffraction pattern. Okay. So if you have a diffraction pattern, this means that the electrons diffracted, which in turn mean that the electrons behave as waves. If the electrons behave as particles instead, a pattern of concentric rings will not be observed. Instead, the particles would actually be distributed uniformly across the screen in this manner. But this is clearly not what was observed. Instead, what was observed was a clear diffraction pattern in the form of concentric rings. In the actual experiment that was done, you have an electron gun that shoots out a beam of electrons so that it hits a thin graphite film. At this point here, your electrons still show particle properties, but after passing through the thin graphite film, your electrons start to diffract, and on the screen that's placed right behind the film, you start to see a diffraction pattern in the form of concentric circles that look like this. So after passing through your thin graphite film, your electrons started showing wave properties. For the concentric rings that you get, the diameter is dependent on the accelerating voltage. What do we mean by that is that if you look at the electron gun, inside the electron gun, there's actually a cathode and an anode between two ends of the electron gun. So that when you have electrons being emitted at the cathode end here, it will be accelerated towards the anode, and then it will eventually leave your electron gun as a beam of electrons towards the thin graphite film. So the accelerating voltage that you have between the cathode and anode here will actually determine the diameter of the concentric rings that you get. So here, what we can say is that a larger accelerating voltage will reduce the diameter of a given ring, while a lower accelerating voltage would increase the diameter of the rings. Since the diffraction pattern is produced when shooting a beam of electrons to a thin graphite film, this proves that particles can behave as a wave. And when you're talking about waves, they must have a wavelength. So de Broglie proposed something called the de Broglie wavelength, which is the wavelength associated with a particle that is moving. The wavelength lambda associated with a particle of mass m moving with speed v is related to its momentum p by this equation, where the de Broglie wavelength is equals to the Planck constant divided by its momentum, or the Planck constant divided by the product of mass times velocity. This is what you call the de Broglie wavelength. If you recall what was mentioned in the previous page, a larger accelerating PD causes a smaller diameter of the ring, whereas a smaller accelerating PD causes a larger diameter of the ring. This can be related to the amount of diffraction you have with a given wavelength. If you look at the de Broglie wavelength equation from before, where lambda is equals to h over mv, Planck constant and mass being constant here would mean that your wavelength is inversely proportional to your speed, such that if your speed were to increase, your wavelength drops, and conversely, if your wavelength drops, your wavelength increases. When you have a larger accelerating PD, this results in electrons with higher speed and hence a smaller wavelength. When compared to your gap wave, you're going to have lesser diffraction, therefore a smaller diameter of your concentric ring. And on the other hand, when you have a smaller PD, your electrons will have lower speed but higher wavelength here. And now when compared to your gap wave, this results in more diffraction, therefore you're going to get a larger diameter of your concentric ring. Okay, so that should be it for your wave particle duality.